All right, so 3.7. Really two topics here, and they're closely related to each other, linearization and differentials. So we'll look at linearization today. Linearization has a key word in it, right? And it's not is, I-Z. It's linear, right? Linear. So lines are the easiest types of functions to work with. Lines are also pretty darn important for that very reason. In calculus, finding tangent lines, it's going to be something we do all year long. Polynomials in general are the easiest functions to work with, and the easiest representative polynomial is a line. Real easy. That's why you start off in Algebra 1 studying lines. So the idea behind linearization is this, and I'll just kind of give you a brief overview. If you have a function that looks like this, let's say it's an ugly function. It's either a really high-order polynomial, or it's like a trig function, or a radical function, or a log function, something that's not real easy to evaluate. The idea is, if I can find the equation of a tangent line at a certain point, call it x equals c, then I can use the tangent line's y values in a little radius on either side of the point of tangency, and I can use the y values of the line to approximate the y values of the curve. Because what I'm really after is what are the function values, the blue values on either side, but it may be like trying to evaluate sine of 15, not 15 degrees, 15 radians. What's sine of 15? I don't know. What's the natural log of 7.3? I don't know. So for weird things like that without a calculator, if I can find an x value, we call it the center of the approximation. It's just the tangent line location. If I can find a value near the one that I like, for which I actually know the value for, I can then write an equation of a tangent line at that point and use the tangent line's y value as an approximation of the function's value. All right. Now, if I stay close to x equals c, then the better the approximation is, right? The difference between the green tangent line y value and the blue is smaller. If I venture too far away, it's not even worth doing because the approximation is horrible. So for a small interval on either side of the point of tangency, tangent line values can approximate function values. Here's kind of something to kind of work out with numbers. If I asked you what the cube root of 70 was, can anyone tell me? For two decimal places. Yeah, most people say 4 point something, right? So that's not really that, like you're walking with friends, hey, the cube root of 70, what is it? It's like 4 point something. Wow, how'd you do that? How did you know it was 4 point something? That's not something that's really all that wowish, right? How do we know it's 4 point something? But thank you for volunteering that. Yeah, the cube root of 64 is 4, and the cube root of 125 is 5. In other words, 4 cubed is 64, 5 cubed is 125. Since 70 falls between 64 and 125, it's got to be 4 point something. And because 70 is actually closer to 64 than 125, it's actually probably closer to 4 than it is to 5, right? It's probably not 4.9. It's probably like 4.1 something. But wouldn't it be cool if, without doing very much work at all, we can get not only 4, but maybe 4.2 decimal places, maybe even 3. That'd be nice if we didn't have a calculator. So that's what linearization is going to allow us to do. Here's how we would analyze the problem. If we look at the cube root of x function, y equals the cube root of x. Why cube root of x? Because we're trying to find the cube root of a number. The cube root function, of course, is a parent function. Remember, it's the one that has the vertical tangent right there. But if I go up far enough, notice the graph is tapering off. What I'm really interested in is what is the y value right there at 70? Well, because 70 is not a perfect cube, but 64 is a perfect cube, and it's in the neighborhood of 70, I can actually then write the equation for the tangent line for this function at 64. And I'll try and draw the tangent line or highlight it right there. Now notice, because this graph is so flat, the tangent line and the function value have the exact same value at 64, right? They share a y value and a slope value. But as we go to the left and right, even though it doesn't appear to be, they're not the same curve, all right? It actually looks more like, let me draw this. If you were to zoom in on that point, it would look something like this. You have a graph that looks like that. Here's 64. And the tangent line would look like this, and let's call this 70. We're actually interested in finding this value, but maybe this value here on the tangent line can be used as an approximation for that one. All right? And notice that if this is kind of drawn to scale, that approximation is going to be a pretty darn good approximation. Now, because the graph is also concave down between 64 and 70, we know the tangent line is going to be above the curve. And so not only will we be able to get an approximation using a linear calculation, we will also know that it's going to be a little bit too big. It's a slight over approximation. All right? So that's the idea of linearization. Let me go ahead and write it down. Values of the tangent line are approximations of function values near, I'll just use that word, near the point of tangency. And that's the whole idea. We're after the function's y values, but they're too hard to compute, and we don't have a calculator, but we need to be a little bit more accurate than just 4 point something. So let's go ahead and actually work this one out. Let's figure out what the cube root of 70 is. Well, I'm going to need to write the equation of the tangent line. So this is something we've been doing all year long. It says to use 64 as the center of the approximation. So again, on your own, why does 64 make sense? It's a perfect cube, and it's near 70. We could also use 125 if we wanted as the center of the approximation, but 125 is a little further away from 70 than 64 is. All right, so now I'm committed to writing the equation of the tangent line at x equals 64. So I need a point, and I need a slope. We've been needing that all year long. So the point is going to be 64 comma cube root of 64, which of course is 64 comma 4, right? Now for the slope, if y is equal to the cube root of x, which is also known as x to the 1/3, I'm going to need the derivative. So let's find it. Y prime, that's going to be 1/3 x to the negative 2/3, power rule. And I'm going to clean it up before I plug in. That's 1/3 cube root of x squared. So now I just need the slope at 64. So I'll plug 64 into both sides. Y prime is 64. And you got to evaluate that. Now, don't feel like you have to square 64 first, right? We go small before we go big. The cube root of 64, again, that's nice. It's 4. 4 squared is 16. 16 times 3 is 48. So the slope way out there at 64 was pretty darn flat. One horizontal or one vertical movement for 48 horizontal movements. So now we can write the equation. The equation of the tangent line then, in Taylor form, is y equals the y value, which remember the y value is 4, plus the slope of 1/48 times x minus the x value is 64. Now up to now we've written the equation of the line and we've walked away. But now we want to use it. We want to use the values of this tangent line in the neighborhood of 64 to approximate the values of the function cube root of x. And because we're going to use it, it's now time to give our line a more suitable name. Y is very generic. So when we use it to approximate, we usually give it a name like capital L. And I like making the cursive L. It's kind of fun to make. L for line, L for linearization. The linearization of the function is just the equation of the tangent line. And the reason it works, remember, is because if a function is differentiable, we've talked about this earlier, it's also locally linear. So as you zoom in repeatedly, you'll not see the curve at all. You'll actually see the tangent line. And so that's, again, the idea behind it, that zooming in, the values of the function near the point of tangency are approximations of the function we want. Okay, so now we want to figure out what the cube root of 70 is, which is the function value evaluated at 70. So here is what we were going to say. F of 70, that is the cube root of 70, is approximated by squiggles, the L of 70 value. So this is where notation is a big thing, right? You're approximating, so you want to make sure you use the squiggles. The actual value, in other words, is approximated by the linear value, which equals. And now all we got to do is plug a 70 in to the equation of the line. 70 minus 64? 6, right? 6 48 simplifies down to 1/8. So we're left with 4 and 1/8, or 4 plus an 8, which as a decimal is 4.125. So there you go. What's the cube root of 70? Well, it's about 4.125. And actually, it's a teensy-weensy bit whatter than that. Bigger or smaller? Should be smaller. So if you look at the concavity of your function in the neighborhood where you're working, we're working in the interval from 64 to 70. Because the graph is concave down like a frown, your tangent lines are always going to be above the curve, and therefore your approximation, in this case, is a slight over approximation. Now, does anybody happen to know what the actual cube root of 70 is? Your calculator does. And I'd be curious to see how your calculator actually computes the cube root of 70. It doesn't reference a chart in its memory and just write it down. It actually computes it. Later on in the year, we're going to talk about Taylor polynomials. And if you know, all year long, we've been calling that version of the line the Taylor form. This is a first-degree Taylor polynomial. It's a line. And later on in the year, I'll show you how you can get the same approximation for the cube root of 70, not by using a linear, but perhaps by using a quadratic equation, or a cubic equation, or a quartic equation, or a quintic, some polynomial of higher degree. And it turns out there's a way to do that. So evaluating polynomials, if they're not linear polynomials, is considered a much easier task than evaluating the cube root of a number or the natural log of a number. And if you go up higher and higher on the polynomial rung, from linear to quadratic to cubic to quartic, your approximation gets better and better and better and better. And because it gets better and better, you're actually able to deviate left and right from the point of tangency a little bit further away. Now, our actual value should be really, really close to 4.125, even though we are jumping 6 units away from the point of tangency. And it's because the graph is so darn flat there. If you type it into your calculator, you will get the calculator's answer, which I believe it calculates by Taylor polynomials. But 4.121, you got it? Thanks. So there you go. We know our approximation was going to be a little bit too big. We just didn't realize it was going to be that close too big. We're only off by 4 thousandths. We were correct to 2 decimal places just by a little linear calculation. And that right there is the whole idea behind linearization. So if it asks you to write the linearization of a function, that just means come up with the equation of the tangent line at that point. Now, because we're going to use it, give it a distinctive name, and then write this right here. This is pretty important. The actual value is approximated by the linear value, plug in, evaluate. And it's a lot easier to leave it in Taylor form, because when you leave it in Taylor form, you always have x minus your center, x minus the x value right there. So plugging in, you're going to be able to chop that number down to size right away by subtracting it. All right. How much time? We got time for one more. Let's look at this one from scratch. What's the 4th root of 17? That's what we're after, the 4th root of 17. Well, let's see. 2 to the 4th is 16, right? And 3 to the 4th is 81. So 16 is too small, 81 is too big, but 16 is nearby, yeah? So I can center my approximation at 16. The 4th root of 16 is 2. And it's probably going to be then, the 4th root of 17 is probably going to be the same thing, 2 point something, really, really close to 2. All right, so this case, does anyone disagree of choosing 16 as the center? What's the criteria for choosing? It's got to be a perfect 4th root, so that we can compute the 4th root of it, and it's got to be near 17. 16, I think, is the closest perfect 4th root to 17. So let's go ahead and write the equation of the tangent line then for the function y equals the 4th root of x at x equals our center, 16. All right, so let's go ahead and just write the point down. That's pretty easy. That's going to be 16, comma 2. Now we need the slope at that point. So y prime is going to be 1/4 x to the negative 3/4. which when you clean it up is 1 over 4 fourth root of x cubed. If you plug in the 16, you get y prime is 16 to equal 1 over the fourth root. The fourth root of 16 is 2. 2 cubed is 8. So you end up with 1 over 32. So now the equation of the line, I'm just going to go straight to calling it L of x. So L of x, the tangent line equation, is the y value of 2 plus the slope 1 over 32 times x minus the x value of 16. And now we can say the function value at 17, that's the actual fourth root of 17, can be approximated by evaluating L, the tangent line at 17, and that's actually going to equal 2 plus 1 over 32nd. Because 17 minus 16 is 1. So as a mixed number, that's 2 and 1 over 32. As a mixed number, that's going to be 65 32nds. And even if you wanted a 3-decimal answer, if you didn't memorize what the stem of 132 gives you, long division is easy to do if you wanted to carry it out to decimals. So now that we have this as our approximation, how are we going to know if it's an over or an under? Right, we need to know if the function is concave up or concave down between 16 and 17, which is where we're working. I don't have the graph of this function, but I know that the second derivative gives me that information, right? So let's go ahead and find the second derivative. Here's the first derivative, still in power rule format. So the second derivative is going to be negative 3/16 times x to the negative 7/4, which if you clean that up, that's negative 3 all over 16 times the fourth root of x to the 7. Which, what do you know about the sign of that function for all positive x's? It's negative. So this is less than 0 for all x greater than 0. Now, if I say greater than 0, does that cover the x interval I'm working on from 16 to 17? Yes. You want to make sure it covers not just the point of tangency and not just the point you're trying to approximate at, but everything in between. So by saying it's the second derivative is negative everywhere to the right of 0, that covers it. So if the graph is a negative second derivative, remember you could draw the little frowny guy with the frowny eyes. That means the graph is concave down everywhere to the right of 0, which means the tangent lines are going to be above the curve again. So now all you have to say is, so L of 17 over approximates F of 17. And that right there is a typical linearization question. The only thing that's going to be different when you start seeing them is you're not going to have to choose your own center. It'll be given to you. It'll say approximate the fourth root of x using the tangent line to the function at x equals 16. And it'll say, is it an over or an under approximation? So you'll be given the function. You'll be given the center for the approximation. All you got to do is write the equation of the tangent line, show the notation with the squiggles, plug it into the equation of the line, and evaluate it. And then look at the second derivative. Is it positive? Is it negative? Because that's going to help you decide if it's an over or an under approximation. If the graph, of course, was concave up on the interval, then the tangent lines are below and it's an under approximation. And now if you're really curious, if you have a calculator, you can actually compute the fourth root of 17 and evaluate 65 32nds. And I have a feeling you're going to be pretty close again. Probably correct the 2 decimal places. Now, what happens if your curve is not concave down? The next question is something like x cubed. So what if we have something like this, and I want to approximate the function value there? Well, if I write the equation of the tangent line nearby, it might look like that. Now notice, because the curve gets really big really fast, I can't deviate too far at all from my point of tangency unless I'm expecting a huge error, right? Whereas for functions that are like this, that are pretty lazily growing, you could venture 6, 7, 8 units away from the point of tangency and still have a really good approximation. So sometimes we're only going to be able to drift left and right, not by 6 units, but maybe about like 6/100ths of a unit. 0.06 or 0.001 or some very, very small value. All right? And we'll see what that looks like tomorrow when we do example 3. We'll stop right there. So there's linearization. Writing equations of tangent lines and then using them to approximate the functions nearby.